So today I'm going to talk about a problem I guess was first introduced to me during my postdoc by Devarat Shah, and it's the problem of collaborative ranking from pairwise comparisons. So it's sort of a fusion of the collaborative filtering problem with the rank aggregation problem. And it's kind of arises in settings where what you observe from different users are not necessarily how much they like something, but that they prefer something over other objects. So more concretely, what we're going to assume is that for different users, we observe partial preferences. So for example, here we might have D1 users and D2 different items, and then for each of the possible n choose 2, or not each, but some subset of the possible D2 choose 2 pairwise comparisons, we see some outcome. So for example, for the question, is 1 greater than 2, user 1 would say no, that's a -1. For 1 greater than 3, user 1 would say yes. So what we observe are these partial preferences, which might arise if a user goes into a store and is purchasing one item over many. You can't stop them and ask them, how much do you like this item? All you can kind of ask them is, all you can know is that they purchased that item over other items. Similarly, in web pages, Google doesn't come back and ask the user what was the rating of this web page from 1 to 5 based on your search. All it knows is you picked a web page over all the possible web pages that it displayed for you. And then so for our goal is to infer each of the user's underlying preferences, and we want to personalize them in some sense to each different user. We don't want one single aggregation that aggregates all the preferences. We want unique ones for each individual. So let's recall that just a standard collaborative filtering or matrix completion problem. And in this setting, what we have are users, and they give ratings to some objects. So for example, in Amazon, users might rate certain books from 1 to 5 stars. And then what we see is that users can't possibly rate every single possible object, and instead what we see a sparse collection of revealed entries. And from that, we'd like to infer the unobserved objects per users so that we can make recommendations or make inferences about what the users actually like. And the problem with this is that it's really misspecified. And so concretely, we have some unknown matrix, theta star, that's D1 by D2. And then what we observe are samples, say n samples, of an entry ij and a noisy partial observation, a noisy observation of that entry. And what we'd like to do is just infer the entire matrix theta star. But we know that if I give you any two matrices that agree on the observed entries, then those two are equally good based solely on the model, based solely on the observations. So in that sense, we need to impose some additional constraints on the theta star in order to make this identifiable. So there's some modeling assumptions that we can make. One is kind of a mixture model. And in this setting, what we have is our matrix theta star. So here I'm taking theta star transpose. So this is D2 by D1. And I might have item weights. So there are basically different components, and each one has a different weight for each different item. And every user is randomly drawn from one of those item weights. So you might think that this user is coming from the blue prototype, and then this one's the green one, and so on. And so basically we have this selection matrix that's just sparse. Each of the columns is one sparse. And now I write this approximate decomposition because there could be some noise. And then there are generalizations of this as well, where we might think that the L1 norm of the columns is 1. So this would be like latent Dirichlet allocation, for example. Another model that we can consider is the low-rank matrix estimation model. And this model is somehow assuming that given users in movies, there is some underlying latent low-dimensional embedding. And so somehow there are some user and item features, and given those, then the rating is just simply the inner product between the user features and the item features. And it should be noted then that the low-rank matrix problem is more general than the mixture model problem, but there are also more parameters that one would need to estimate. While both need to estimate these item weights, so this matrix here, the item features, these are mixed, but the selection matrix for the mixture model is much simpler than in the low-rank matrix estimation problem, where we're allowing arbitrary values to be in that matrix. Now, the key point about the matrix completion setting is that we directly observe the noisy entries of the matrix. So now for us, we're considering comparisons data. And then these for us are natural because in many contexts, all we know is that the user might prefer one item to another. Say if they watch one movie at the movie theater instead of another, or on Netflix, they watch one movie or another. Say, for example, in tennis, you might know that's one player beats another player in Wimbledon, but they always lose at the US Open. And you want to understand, well, what are the latent features that are driving the success based on, say, the user in this case, in the tennis case, being Wimbledon or the US Open. And one thing that's nice about rankings is that they're in some sense universal. So suppose I had one person, a user, that say only ever had Dunkin' Donuts or Starbucks coffee and say never went to Italy and tried a cappuccino. And then in his sense, say Starbucks is a 5 and Dunkin' Donuts is a 3. Now when he goes to Italy and has an espresso and realizes he was wrong all his life and that there are better things out there than Starbucks, all he can do is rate the cappuccino in Italy as a 5. And now that's equivalent. The Starbucks and the cappuccino are equal. Whereas in the preferences setting, all the person would have to say is, oh, this cappuccino is much better than Starbucks and much better than Dunkin' Donuts. And then somehow it's able to automatically readjust itself. Now, one of the problems with rankings, as opposed to ratings, is that they're hard to aggregate. If I just have ratings, I could just take an average. That's simple, in just a single case. For rank aggregation, in general, it's quite hard. And we see many real-world examples of this. Say, the FIFA World Rankings for soccer are terrible. Same with college football. There's always inconsistencies. And even now, college football is introducing a playoff system to make it a little more fair. So what is the rank aggregation problem? So in this context, we might have, say, soccer teams that play each other, and all we can observe is the outcome. And then from that, we'd like to find some aggregate and make a decision. For example, who's the Premier League champion, who's second best, who's going to go to the Champions League, etc. And now this is a setting where we only want a single aggregation, and on its own, this is still pretty hard. So coming back to the individualized rank aggregation problem, it kind of itself also looks like a matrix completion problem. I have users, and they're telling me a +1 or a -1 of what happens for these pairwise comparisons. So it's if I need to do matrix completion in a D1 by D2 squared matrix. But that suddenly makes things a little bit harder. This is maybe a little bit too general than we'd like to assume. So we want to impose some additional structure on the pairwise comparisons and look at how they're actually generated. So to that end, we consider some choice models for pairwise comparisons. So there's one perspective, which is sort of the rational view, or the axiom of revealed preferences, which basically assumes there's one sort of true preference for everybody, and they're always rational, and they always pick the right best thing. But we know that's probably unlikely. We might all know that, say, Brazil is better than Germany, but sometimes Germany might destroy Brazil in World Cup games in their home country. Another perspective is, so that gives us the probabilistic view. So in the probabilistic view, we might assume parametric models, say due to Thurston. And the model that we're going to consider is the Bradley-Terry-Lucci model, or just the M&L model. And so this model was used by McFadden for figuring out where to put BART stops in the Bay Area. It's also used in airline scheduling. Xbox uses it to rank its players, and it's also the basis of the chess ranking system and the chess scores. And basically, the model is very simple. We assume that each user I has a true underlying score for item j, and that's theta star ij. And then the probability that user I prefers item j over item k is just e to the theta star ij over e to the theta star ij plus e to the theta star ik. So it's a really simple model. There are more general ones that look at the differences of theta star ik minus theta star ij, but we'll just consider this simple case in this context. So now we can write down the full model that we're going to consider. Is we're going to take theta star to be approximately low rank. So this captures the mixture models as well as the low dimensional embedding models that we were considering. We're also going to assume that the Frobenius norm of theta star is upper bounded by 1, and this is for normalization. There's also another point, and it's that for identifiability, we'll need the rows of theta star to actually sum to 0. And that's because, well, when we look at the probability of y sub I, it's only dependent on the difference between the theta stars in individual rows. So that is, for observation I, and we're going to assume we have n observations, we see some user ui, and some items ki, ji, and some outcome yi. And then for us, the ordering matters. The question is, was ki preferred over ji? And then +1 if yes, 0 if no. And then so it should be noted that this same model was actually considered in some parallel work by Siwoong Oh at UIUC and Devavrat Shah at MIT, and we'll discuss their results in a bit. So now the algorithm that we use is very simple. It's just a penalized maximum likelihood estimator. So all we're going to consider is that our estimate, theta hat of theta star, is just some argmin over theta of the maximum likelihood plus a nuclear norm penalization term. And then here, this is just the standard log likelihood. And then the nuclear norm is the sum of the singular values of its argument. And it's been shown both empirically and theoretically that the nuclear norm does a good job of encouraging the solution theta hat to be approximately low rank. And then so given this simple algorithm, we can provide some analysis. In order to establish the theory, we assume that users and items are sampled uniformly IID. So the distribution over items can be relaxed to a sort of weighted distribution, but we're still assuming then that the items are picked independently. Now if we let D to be just equal to the average dimension, so D1 plus D2 over 2, and then we also have to define this function psi of A, which is equal to psi of alpha, which is equal to e to the alpha over 1 plus e to the alpha squared. So this is basically just the variance term of a Bernoulli. Then we have the following result. Suppose that we set the regularization parameter lambda to be 32, that was kind of arbitrary, but 32 root d log d over n. Then any solution theta hat to this convex program satisfies the following upper bound. It says that theta hat minus theta star in Frobenius norm is upper bounded by some constant times the max between alpha and 1 over psi 2 alpha times the max between these two terms here. So in this theorem, we actually don't make an assumption that theta star is low rank. Theta star can be anything. And it's a trade-off between these two terms, a root r d log d over n term and this term here. So this result holds with probability at least 1 minus 2 over d squared for any r. Now, you never have to set the rank in this algorithm, but the upper bound at least will optimize. You would, if you wanted to use it, you would find the minimum over all such R. And the penalty in this error decomposes in a nice way. Basically, this is the error for estimating a rank R matrix. Because if you think about it, a rank R matrix has roughly RD1 plus RD2 free parameters. And this is roughly the parametric rate for estimating RD1 plus RD2 parameters. Now this term here is a penalty that we have to pay because we're trying to approximate our theta star matrix by a rank R matrix. So we're paying some penalty in the L1, in the sum of the singular values beyond the rth one. So here we're assuming that the singular values of theta star are sorted in order. Sigma 1 is the operator norm, or the largest singular value of the matrix. So we can look at some simple corollaries. The first is if we're in the exact low rank setting. So in this setting, suppose that theta star is just low rank. That's what we know. We also know its Frobenius norm is bounded by 1. In that case, the Frobenius norm squared is just this constant here. We're going to assume alpha behaves like a constant times RD log D over n. And that's when theta star is just exactly low rank, and we don't know anything else about the singular values. In another context, we might consider the case where the singular values of theta star are weakly sparse. So one example is they belong to an LQ ball for Q in 0 to 1. And this is just the sum over of the singular values raised to the qth power. And we let BQ RQ to be the set of theta such that the LQ norm is bounded by RQ. And so in this case, when Q is equal to 0, this is just sparsity. This is just counting the number of non-zero singular values. And that's just what a low rank matrix is. That would be the rank of the matrix. As we increase Q, it starts to allow for lesser, more dense rank. And in that case, if we suppose that theta star is in an RQ ball, then we obtain the following upper bound. It says here that theta hat minus theta star Frobenius norm squared is upper bounded by RQ times, again, this max term here, times d log d over n to the power of 1 minus q over 2. So in this case, we exactly recover the result, the low rank matrix result, when q equals 0. And then we see that the upper bound gets worse as we increase q. And that's natural, because as the problem becomes less sparse, it should become harder to estimate a low rank matrix when it's not low rank. So one thing that's interesting and to note is how these results compare to, say, the standard matrix completion results, where we have direct observations of the entries themselves. And so we assume the exact same conditions as in the previous slides. We're assuming that the Frobenius norm is bounded by 1. There's also this L infinity bound of alpha. And in that case, say the theta star is rank R, then theta hat minus theta star in Frobenius norm is upper bounded by alpha root RD log D over n. So barring this additional term here, they match. The rate is actually matching. And then what's also interesting to note is that there's a minimax lower bound that one can show if theta star has rank R and it also satisfies a spiky condition, then the min over all possible theta hats, regardless of computational complexity, and the max over all possible theta stars, the expected value of the error, is lower bounded by root RD over n. So we've sort of been able to exploit the model assumption, and we've moved this D1 squared matrix completion problem to basically the same D1 by D2 matrix completion problem. So we can now also compare the results that we have to those established by Siwong Oh and Devaraj Shah. In their algorithm, it's an interesting algorithm that's based on tensor decomposition, methods on of the third order moments, basically. It's doing a method of moments. And their goal is just to estimate the item weights W. So recall that in the mixture model, what we have are different item weight components. Oh, that should be theta star transpose. We have different mixed item weights, and each user is one of these item weights. And now, given those item weights, Owen Shaw assumed that a user will provide L pairwise comparisons from the exact same model that we had established. And what they're actually able to show is that you would need R to the 3.5 times D1 cubed samples for item parameter recovery. So this is in contrast with our result, which says if you want to recover the entire matrix, you need R times D1 plus D2 samples. Now, while their scaling in R and D1 are quite large, it should be noted that they have no dependency on D2, at least in terms of error behavior. All they require is that there are a sufficient number of examples. They need D2 large enough, or sorry, D1 large enough, that should be D2. And they need, so that's D2, and they need D1 large enough so that they have enough users' preferences to see all of these items. So it depends on what type of regime you're in and what the problem is that you're interested in understanding. So for us, we can give a quick proof of a quick proof sketch. And in our context, we assume in this proof sketch that theta star has rank R. And it basically uses the restricted strong convexity and decomposable regularizes idea that we developed in some previous work. And so the main difficulty comes in proving that this loss satisfies a restricted strong convexity condition. And all that means is that for any delta in some restricted set, which I won't define, but there's a restricted set that we care about, the first order Taylor approximation, the error around theta star, is lower bounded by some gamma times the Frobenius norm of delta. So this is basically telling me that if I'm at theta star and I move in one of these restricted directions, I'm actually going to see a change. So this is in contrast if you just considered matrix completion and you allowed your error to move in any direction. If I moved in the directions of unobserved entries, the loss would never change. I'd somehow be in the null space. So what one needs to establish is that for the set of restricted directions, there is some level of curvature. And then, so with that restricted strong convexity, one can basically show that the error in Frobenius norm is upper bounded by 1 over this restricted strong convexity parameter times root the rank times the operator norm of the gradient of the loss at theta star. So to establish all of these, you use some high probability results in empirical process theory to prove that this would hold with high probability, and similarly an upper bound on the operator norm of the gradient of the loss at theta star, and then that would yield the results that we established for this problem. So in conclusion, what we have is an individualized rank aggregation algorithm, so which is generalizing just standard rank aggregation. And it's sort of, as far as I know, the first analysis for this problem. It works in the high dimensional regime. That is the regime we're assuming where the number of observations are much, much less than the number of parameters, which is D1 times D2. And then what's interesting is it matches the minimax optimal rates for matrix completion. And it should also be noted that these results, they easily extend to the 1 out of L selections scheme. So if I have L items and I pick one of them out of the L, we get the exact same results. What would be interesting is if we can extend these results and show that if you're only interested in the item embeddings, we can potentially get, well, hopefully get better convergence behavior for the item weight recovery. All right, thank you.